Can I welcome you to the Isaac Newton Institute? My name is Ben Mestel. I'm the Deputy Director of the Isaac Newton Institute, which is the UK's premier mathematical sciences research institute. It runs 4 to 6 programs every year on high-level mathematics. There are 2 going on at the moment, but today we've got a special day for the Cambridge Science Festival. I just want to announce a few things before we get on to the talk. The first thing is, could you fill out the evaluation form that's in front of you? I know some of you at the back won't have one, but if you could please fill out the evaluation form. There's a desk outside where you'll see some memorabilia for the Isaac Newton Institute. Do have a look at the desk, and if you'd like to purchase some things, then my colleague Stephen will be out there to help you do that. At the end, if you haven't done it already, if you could sign the visitor's book, it's very useful for us to keep a record of who visits the Institute. There are some instructions for what to do in the event of a fire here, which I hope you can read. I'll read it out briefly. Operate the nearest fire alarm. Leave the building by the nearest safe exit, which are these doors here, by the way, and report to the assembly point, which I believe is outside there. Can I ask you to turn off your mobile phones if you haven't done that already? Thank you. And finally, we are going to record this talk, and it will be available for download on the web later on. I should tell you, I've got to read something out to you. The photographs and films will be used by the University of Cambridge for the purpose of promoting its Science Week activities and may be published on the university's website and on other websites and passed to third parties in the press and broadcast media. If you do not wish to appear in the photograph or films, please avoid this area. So you can leave to be in. Thank you very much for your cooperation. Okay, I think that's all the formal business. I'd like to extend a very warm welcome to Professor Franco Vivaldi from Queen Mary University of London. I've known Franco for many years. He's been a very important researcher in dynamical systems theory for over 25 years. He's an expert on the mathematical theory of chaos, and we're very fortunate to have him here to talk about the arithmetic of chaos. Franco.
Sorry, let me just switch this off. Can you dim the lights, please? Okay. Well, thanks very much for coming here, and thanks for the Newton Institute for giving me the opportunity. It's not switched on. Do you read me? Roger, over. Can you turn it up a bit? Okay, well, I will shout. Okay. So, this is a talk about the arithmetic of chaos. Well, I'm not trying to explain you what the arithmetic of chaos is just now. But let me start with something else, the theory of dynamical systems. Dynamical system theory is a branch of mathematics. It's been around for a long time. It's been around for 300 years. And the goal of the theory of dynamical system is to predict the future. And Newton was one of the first that wanted to predict the future using mathematics. And the theory of dynamical system has been very successful. Their main concern for many, many years was to predict the motion of the planets. And they achieved quite spectacular results. For instance, now we can predict the event such an eclipse with clockwork precision. However, in the past 30 years, which if you think about it, over a period of 300 years, just the last 10%, people started realizing that is not always possible. Yes, we can predict eclipses, but if we want to predict earthquakes, or indeed the weather, then there are problems. And So about 30 years ago, there was some kind of turning point in the theory of dynamical systems. People started studying the reasons why you couldn't predict the future. And that got a label attached to it. It's called chaos theory. You probably have heard of chaos theory, the butterfly effect. It got to the popular press. And so somehow now there is this awareness that this presumption that the future can be predicted, given that the rules of the games are clear, it's really a presumption. This cannot always be achieved. Now, I'm a mathematician. I'm interested in the mathematics of it. So this talk is going to be of the mathematics of non-predictability rather than the physics of it. Now, it turns out that if you're interested in the theory of chaos, you get into deep waters very, very quickly. And what I'm going to be talking about today will actually have something to do with very advanced topics of contemporary mathematics. For instance, complexity theory. And other topics that may be a bit older, but they still belong to postgraduate mathematics. For instance, measure theory. And you may wonder, what's my plan? And this is postgraduate mathematics. But it turns out that the basic ideas are actually very, very, very simple. And so it is my hope to be able to get across this basic idea and to explain to you what is the ultimate origin of our inability to predict, which, to cut a long story short, will lie in our inability to know the basic objects of mathematics, which are the numbers. Now, I will start from the very beginning. I will not assume any mathematics background at all, apart from perhaps addition and multiplication. I will not assume any knowledge whatsoever. We start from zero. We start from the very beginning. We start from God. Now, what does God have to do with all this? And what does God have to do with arithmetic chaos and all that? Well, through the course of this talk, we will probably understand this a bit better, but as an opening shot, let me quote a 19th century mathematician, Kronecker. He clarified the basic position between God and mathematics. God gave us the integers, and the rest is a work of man. Now, it looks simple, right? But it isn't. So now let's start examining the work of man. So God gave us the integers. What do you do if God gives you integers? I mean, when you're small, 2 or 3 years old, you start counting, so you already have the integers. What do you do with them? You can do all kinds of things, but what man did was to put them on a line. You don't have to put the integers on a line, but that's the obvious thing to do. So you got 0, and then 1, 2, 3, 4. These are the object of counting, and then later on people started thinking about the negative integers, which are on the left. If you have a small integer, it's an integer that is sort of around there. And integers 100 miles to the right are large integers, and then there is a spacing between them. It's 1, they're distance 1 from each other. You could put them somewhere else, not on the line, but for the time being, let's put them on the line. And in fact, that is going to be a very familiar environment. So what do you do after putting the integers on a line and just noting that they are 1 apart from each other, consecutive integers? Well, you try to fill the gaps. You can't fill the gaps with integers, so fractions come into the game. So a half, 1 divided by 2, where is it? Well, you measure the distance from 1 to 0 divided by 2. And so 18 over 7, you measure the distance from 18 to 0, and you cut it by 7. And so you start occupying the space in between integers. So you see, you can be in the middle in between two integers. This one is just a bit on the right of the middle. Or if you want an integer in between 0 and 1/2, a number in between 0 and 1/2, you can certainly manufacture a fraction in there. You could put a fraction right there, you could put a fraction there, you can put a fraction close to anywhere you want. with a little bit of practice, it's actually not easy. If somebody would ask you, where is 183 over 77? You'll see it's somewhere, right? But you have to position it. Right? This is not so easy, it turns out, and for very deep reasons. But you can sort of believe me if I tell you that you can put fraction just about close to everywhere. Now, the ancient Greeks thought that was the end of the line. But then somebody started thinking, oh, wait a minute, there are numbers which are not fractions. The first guy who had that brilliant idea was actually put to death because the other Greek philosophers thought it was, no. All there is the integers and then one integer on top of the other. But now we know that there's a lot more than the integers. So square root of 2 is a baby theorem that if you read mathematics at university, you will see in the first year. Square root of 2 is not a fraction. You can't write square root of 2 as something or something else where these two things are integers. And that's also positioned somewhere on the line, but it's not a fraction. On the other hand, square root of 2 is that thing that if you square it, you get 2. And this recipe, that thing that if you square it, you get 2, has got some fancy names called algebraic numbers. They're numbers that somehow they're friends of integers and fractions. They're very close. But then people started realizing that that is not the whole story. And pi came about, and then this is a much more difficult theorem to prove. Pi is not a fraction, and it is not even the sort of numbers like square root of 2. It's called transcendental number. You cannot write a simple equation for pi. You have to bring in infinite processes. But that too belongs to the zoo of objects that man constructed just from the integers. Now, what is the typical member of that zoo? Well, not one of these, the sort of number that you see here. These are the baby numbers. These are the numbers that you and I deal with on a sort of daily basis. If you do mathematics, if you study mathematics, you will deal with 2 pi and a half, and maybe 18 over 7. But that has nothing to do with what's in here. And you don't have to go away from fractions to figure out what's in there. If you want to see a typical member of that zoo, it would be something like that. So, that is much more normal, this number here, than a half over 18 over 7. Now, if I ask you to position that number on the line, then you have one hell of a problem. Now, okay, if you think about it, then, well, we're lucky that we actually have them on display. And just by inspection, we can figure out that they have the same number of digits. If I would give you the numerator and then, next slide, the denominator, you wouldn't have a clue. But now you know that these two numbers have the same number of digits, and so you see you've got here a 59, and here you got a 30. So the numerator is about twice the denominator, just a bit less. So this number, in fact, is just before 2, but you wouldn't, if there were this lucky coincidence of having the same number of digits, you just wouldn't know what that number is. It will keep its secrets. So we have to get accustomed to the fact that when you deal with numbers, you really deal with amazing amount of information. Somehow we have to find ways of processing that information to figure out what that number is telling us. So this is the final stage of the work of man. So the work of man, starting from the integers, is to construct the continuum of the real number system, is to fill all the gaps in between the integers, leaving nothing left. The continuum is something that you can draw with a pencil without lifting the pencil from the paper. What does that mean? It means that for every point on a line, the line where originally we put the integers, there is a number actually. So if we intersect two lines, we can actually characterize the intersection point with one number. That number would have a certain degree of complexity, would have a certain number of information associated with it, which probably would depend on the amount of information that line contains. Now that we've got a continuum of numbers, and every point on this line corresponds to a number, then we can do standard continuum mathematics. When you do derivatives, when you do integrals, which is part of the A-level syllabus, you're actually using as a substrate this continuum of the number system, which is the end point of a process of filling in gaps that started with the integers. This process was actually completed in the second half of the 19th century. It took quite a lot of effort to figure out that you can actually associate a number for every point on the line, although this looks pretty intuitive in a certain sense. Okay, let's shift to dynamics. So dynamics is the science of things that move. What do we mean by moving? Well, the modern view of dynamics, it's more like watching the frames of a film. It turns out that this is a very fruitful approach. So we will not think of going from the present to the future in a sort of continuum of time, but rather by going from one frame to the next. You just watch a film. We're not concerned, because we deal with mathematics, what is the time interval between frames. In a normal film, you get 24 frames a second. We don't care. Let's say a frame every second or every year. It doesn't matter. Just every unit of time there is a frame. And we watch these frames. Now, when you have a dynamical system, you have a rule that takes you from one frame to the next. It's called determinism. In other words, from one frame to the next, there is no uncertainty. There is no cheating. If I start from a frame, the next frame is going to be determined. And so all you have, that is called the law of motion. What takes you from the present to the sort of immediate future. Then you keep doing that. You apply the law of motion to this point here, will take you there, then it take you there, then it take you there. And then you decide how far in the future you want to go. And so you get this bunch of arrows or this bunch of processes that take you from the initial frame to frame number whatever. And if you can figure out what's on that frame, then you can predict. You can predict the future. So that's the main goal of dynamics. Now, you're not going to see points and arrows in a real situation. In a real situation, for instance, you want to predict the weather, then you've got data, and these data are temperature and pressure of the atmosphere. And then you put this data in the computer, and the computer starts processing them. And it goes through these steps. And these steps for the weather are probably of the order of seconds or fractions of a seconds, and you do millions and millions and millions and millions of steps, and then eventually you pile up a sufficient number of fractions of seconds to get to tomorrow, and then you get to tomorrow's weather. So this process here, for the weather predictions on a computer, will involve millions of little steps, and each step will involve an unbelievable amount of data. But the idea is very simple. It's always the same. You've got numbers. From one number you get to the next number. From one set of numbers you get to the next set of numbers. You keep producing numbers. And this arrow, which takes you from a frame to the next, is just a rule for turning a number into another number. And so predicting the future is very simple. Well, given this, 140, 523, where will I be in 5 steps? You have to be able to figure this out from that and the nature of the arrow. This is the goal of dynamics. Okay, so what we're going to do now, I'm going to describe a toy model. A toy model, it's not, I mean, toy models play an important role in the development of mathematics. These are somehow the essence of a mathematical phenomenon stripped of all the irrelevant things. In mathematics, you don't try to do things. I mean, when you're looking at the heart of things, you don't try to make them realistic of anything. You really want to focus on what counts. And I'm going to introduce a toy model which is unbelievably simple. You would be surprised how many research papers have been written on that model. And you will be even more surprised on how many unanswered questions are about this model. So this is as far as I will stretch your mathematics. Multiplication by 10. Now, you see, I've been kind to you. I didn't say multiplication by 9 or by 11. I said multiplication by 10. Why? Well, because we represent the numbers in base 10. Maybe if you were from another planet, you represent the number in base 29, then I would say multiplication by 29. But here we represent the number in base 10. And so multiplication by 10 is just shifting the decimal point. You wouldn't be able to multiply 0.4073 by 9 in your head, but you can certainly do it by 10. Just move the decimal point to the right. So that would be a rule. How do you turn a present, which is just a number, into the immediate future, multiplied by 10? And then we apply the rule. It turns out that this is going to be pretty dull. So if you start from 0.4073, which is a number in between 0 and 1, in between the first two integers, and then you multiply by 10, you get 4 point something. Then you multiply by 10, you get 40 point something. Well, the first number is 10 times the original one. The second number is 100 times the original one. The third number is 1,000 times the original one. You keep going, and what happens? You shoot off to infinity very, very, very fast. So on the number line, if you just see this dynamical system, sort of zipping numbers to the right, it's not very exciting. Predict the future of that, well, easy peasy. No matter where you start, you're going to go to infinity, unless you start at 0. So that is a very simple dynamical system. What we're going to do, we're going to make it slightly more interesting, but not more complicated. And in order to make it interesting, you have to do a very simple thing. It's got a funny name. It's called modular multiplication. So if you want to look good at a party, say, I'm interested in modular multiplication. In fact, it's really easy. When you multiply a number between 0 and 1, you're going to get something to the left of the decimal point. You just throw it away. That's modular multiplication. So it's not very deep stuff. So let's look at our number, this 4073, and multiply by 10, but every time we just throw away the digit that happens to be on the left of the decimal point, or this number here, 1, 2, 3, 4, 5. They multiply by 10. Well, it would be 1.2345, but we junk the 1, so we get 2345. And multiply by 10, and you get 0.345. And then you keep multiplying, and you keep junking numbers. So what happens? Well, all these numbers, they're all between 0 and 1, because it's 0 point something. And you can sort of try to figure out where they are, right? This is 0.1. The first number is somewhere here on the left. The second one is a bit more to the right. The third one is here. They seem to be marching to the right. Now, if you think about it, you can sort of, well, you can just invent your own digits and try to figure out how these various numbers will just hop along. They will just move between 0 and 1. We jump around. And pretty soon you will understand that by choosing these digits carefully, you can make them do all kinds of crazy things. For instance, sticking around these points for 20 minutes, then going on the right, then coming back, then going 29 times on the right, then in the middle, then doing all kinds of crazy stuff. You can actually manufacture behavior just by putting digits in the right place. Let's think about it a bit more carefully now. Let's just move to the heart of the matter, which is chaos. So, what happens if we want to predict the future of this model? What happens when they want to predict tomorrow's weather? Well, they look at the reading of all these probes, and they get temperatures and pressure. What do they get? Well, they get numbers, right? How many of them? Well, they typically get numbers with 10 figures. Numbers like this. Not more than 10 figures. In some experiments, some laboratory experiments in atomic physics, you may get a bit more than 10 figures. But experiments, you will be super lucky if you get 10 figures. Sometimes you get one figure or two. However, somewhere along the line there's going to be a question mark. That is where your knowledge of the present stops. And now what we're going to do, we are going to run on a computer this baby model, the toy model, and see what happens. Well, it's very easy to see what's going to happen. We multiply by 10, we shift, and junk the digits on the left. What do you see? What are you going to put here, the last place? Well, it's a second question mark, which I didn't put there. And so suppose you just bought your new computer. You spend all your savings, right? It's a fantastic machine. It does 1 billion operations per second. You ask this machine to predict the future. In a fraction of a second, it will go from here to there, and from that point on, it will produce garbage and only garbage and meaningless garbage. And all you have asked that machine to do is to multiply something by 10. So you see, what's the problem? The problem here is this relentless, it's this relentless progression of ignorance, of our lack of knowledge of the system, which marches to the left at an amazing speed, is exponential. It's called exponential instability. When you see straight lines across digits, that's actually an exponential function, and this is wiping out our knowledge of the future very, very fast. So I mean, this is the essence of chaos. Our ignorance of the present, which is right there, hidden in the decimal digit that nobody cares about. It's brought to center stage at an amazing speed. That is what this thing is. So, well, can we beat chaos? Now here we have to make a distinction between mathematics and physics. There's a big distinction. Because in physics we measure. So if you do a measurement, then you're stuck. You know you're not going to achieve infinite precision. In fact, you know you're not going to achieve an arbitrary precision. If somebody asks you to measure a length with 100 digits accuracy, you just would not be able to do it, even if that quantity would be very well defined. But in mathematics, we can bypass that problem. In mathematics, we compute. So if we want to predict the future of this particular toy model, starting from the point square root of 2, the point square root of 2, it turns out, has got infinitely many non-repeating digits. Well, you can compute them very well. It turns out you can compute them with fantastic accuracy. There is a method which is they're called superconvergent. It's like Superman. There are some algorithms that will allow you to compute billions, zillions of digits of square root of 2 without any problem. So if you want to know what is the future of the toy model after 200 iterations, well, no problem. Well, that's the future over there, right? All you have to do is just to go down the digits further and further to the right until you find the digits that are sufficiently further to the right to match your time scale of prediction. And then you can read the future right there in the present. So we know exactly what's going to happen after 200 iterations of the toy model. That is going to be a point 0.4327, blah, blah, blah. We know exactly where it's going to be. So it seems that in mathematics, we can really beat chaos. But the punchline, and this is what I want you to concentrate on, is that to predict the future, we have to be able to compute the present. So this game we win the game, provided that we can get to that 200 digits with some kind of theory, some kind of algorithm, some kind of method which is reliable, and it gives us the answer. All right, so let me try to crystallize what is going on here by quoting an American physicist, the late Joseph Ford, who was one of the gurus of the development of chaos theory. And when he used to introduce this concept back in the 70s, when nobody heard about it, then he used a very interesting sort of parallel with relativity and quantum mechanics, which have been the two major revolutions in physics in the 20th century. And Joe used to say that people thought that fast is like slow, except faster. But then relativity came and showed that fast is different. So if you go fast, I mean, if you go 100 miles an hour, then it's more or less the same as going at 10 miles an hour, except 10 times faster. But then if you start approaching the speed of light, then all kinds of weird things start happening. Your intuition goes off the window, and it is an entirely new set of phenomena that take place when things are very, very fast. Now, quantum mechanics did sort of the same thing about length. People thought the small is like big, except smaller. But if you operate at a very small scale, at atomic scales, when the quantum phenomena are relevant, then there is a completely weird set of phenomena that take place and that defeat intuition, just like relativity on speed. Well, chaos is there is some sort of terminal distinction between something chaotic and something very complicated. And Joe Ford put it like this: people thought the complex is like simple, except more complicated. But then chaos came along and showed the complex is different. And this is what I want to deal with next. So this is a beginning of what is called complexity theory, but it's a really fancy name for something very simple. Suppose that we want to build numbers. Remember, on the previous slide, there was the square root of 2 with all these digits. How do you build them? Well, let's try to build something a lot simpler than the digits of the square root of 2. Let's try to build a number of 45 digits. And the number is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. The 1, 2, 3 is repeated 15 times. Now there are, if you you don't have to be a guru in computer science to figure out sort of how to do that. There are at least two ways of doing it. One is to just put a print command. Just print this. You type the computer program and then you run it and it prints 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Or you can say print 1, 2, 3 15 times. Now, what's the difference between these two programs? How do you synthesize the difference between these two programs? If you want to see what I'm after, think about print 1, 2, 3 15 million times. Now, the bottom program will have would change a little bit. The top program will change a lot. How would you synthesize the difference between these two programs? One is dumb and the other is smart. You wouldn't think of typing 1, 2, 3, 1, 2, 3, 1, 2, 3 15 million times. You just wouldn't. So this is, in a sense, the essence of complexity theory. Let me just go one step further. That's the number. How do you produce it? Well, everybody knows how to do that. Everybody. Will a smart guy come along and say, that's a waste of time. I know how to do it with a program this big. It turns out that actually this number here can be written with a program small. I won't tell you what it is. But then again, by just modifying one digit, and the program would not work, sort of. So now we have to somehow build some mathematical idea behind the notion of a dumb program and a smart program. And the guy who did that was a very prominent Russian mathematician called Kolmogorov, that in the middle of the last century, he put on a firm foundation the sort of probability theory and the notion of randomness. And he produced a rigorous definition, which is a number, just think of a bunch of digits, is random if the shortest program that can build its digit is the dumb program. In other words, a number is random if no smart guy will ever come around and say, you don't do it that way, you do it with this baby program. You're wasting your time. Now, I haven't touched the issue of, if I give you a number, tell me whether there is a program that is more efficient than the dumb program. The dumb program is always available to you. That is a very difficult issue, it turns out. But however, this is a perfect definition. Whether you can decide whether a number, whether the shortest program is the dumb program or not, it's a different matter, but that's the definition. And so Kolmogorov then went to the obvious step of looking at very, very long digit strings. So a random number is a number that can only be produced by the dumb program. The dumb program is roughly as big as the output. You see, the only difference between the dumb program and the output is this print, open parenthesis, close parenthesis. It turns out that that is really dumb. It turns out that you can always do a bit better than that. I mean, if in your program you see some kind of little pattern, then you can sort of get some little discount. But this discount don't do much for you. So the shortest program that you can write for a random number is roughly the same length as the number that you want to produce. In this slide, I indicated that you can make it a bit smaller. On the other hand, if you have a baby program, a very short program that produces a very, 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 very long number, then you will have a scenario such as the one I have indicated here. And now imagine, and this is what mathematicians do, you just consider longer and longer and longer and longer and longer and longer strings. You let the length of the string go to infinity, and then you see the relative length, the length of this divided by the length of that. Now, above, you will get something of the order of 1. I mean, they're roughly of the same length, and so if you divide the numerator by the denominator, you get 1. And here you will get something that will go to 0. So that is the mathematics behind it. So let's look at the essence of it. So we try to represent digits, and we try to find patterns, and we try to exploit the pattern to have a recipe for constructing digit, and we define a random number, a number for which there's no recipe. Okay, before we can get to the punchline, let me describe another major advance in mathematics that took place about 100 years ago. It's called measure theory, but what measure theory really tries to do is to export the concept of mass to the number system. I mean, do numbers have mass? What a stupid question. Of course, they don't have any mass. It's not physical. Well, what do you mean? You know, if you're a mathematician, you say, well, you know, this is irrelevant. Can I define a notion of mass that is consistent? Well, you know, this is the number line. It's over there. And this is the line that we drew with a pencil without lifting the pencil from the paper. And there are the integers 0, 1, 2. And so we decided, well, what is going to be the mass of the numbers? Well, let's start from the obvious definition. This, by the way, the French guy called Lebesgue was the person that started thinking along these lines. Well, the interval between 0 and 1 is of length 1. Let's say that it's got 1 kilo, that weighs 1 kilo. it's pretty sensible. I mean, you could also choose 3 tons or 1 pound or whatever. It wouldn't make any difference. It's not the absolute value that you attach to that weight or mass that is important. Just to have one. And then another thing that you need to put into the equation is that if the numbers that lie between 0 and 1 weigh 1 kilo, then the numbers between 29 and 30 also weigh 1 kilo. In other words, this number line is just uniform. And you don't need anything else. So, you can just start doing some simple inferences. You get a little baby interval. It's shorter, and so it's going to weigh a bit less. And if you measure it, then you know exactly how much it's going to weigh. At this point, what this guy Lebesgue did, he applied the sophisticated tools of analysis that about 100 years ago they were already in a very high degree of development, and he started just using this very simple concept and just carrying them to the natural consequence. And the first rather stunning result is the following: that the total mass of all fractions is 0. So you can actually construct a little theory with a little calculation that will involve the process of a limit that will allow you to weigh the fractions. So you think of the fractions, right? The fraction lie on the number line, and they are arbitrarily close to everywhere. Think of the fraction as some kind of dust. There are other things apart from fractions, but what Lebesgue discovered is that this dust is an infinitely fine dust. It doesn't weigh anything. So in terms of their importance, their weight, the numbers that we are most familiar with, the integers and the fraction, don't count at all. They don't weigh anything. Where is the mass of the number system? Is not with the fractions. Is it with the square roots? Is it with number like pi? What kind of numbers contribute to the mass? So now let me get to the real point of this talk, which is this. Now this is not a computer malfunctioning. This is the heart of the matter. I'm going to be talking about dark matter. Now, dark matter has been in the press for a few years now. So what's the idea? Astronomers started looking with telescopes, and they started observing various things. They started counting stars, figuring out the mass of the stars, the mass of the galaxies, and then by looking at the motions of stars, say around galaxies, they realize that there is a discrepancy. That somehow there is something in there that contributes to the overall gravitation of the universe, which we can't see. And they started estimating how much of that is around, and that is the ratio between what we can see and what must be there what we cannot see is very unfavorable to us. Only few percent of what we see of what's in there can be seen at the telescope. And people start fighting about, well, this is 4%, 5%, 9%, and nobody has a clue, and every other week the theory changes, and the situation is very unsatisfactory. What doesn't go on the front page of the newspapers is that the situation in mathematics is a lot worse. But because behind it there is complexity theory, and there is measure theory, and all that kind of stuff, the journalists don't even want to get close to that. But what should be on the front page of a newspaper is this: that the overwhelming majority of the real numbers are invisible to us. In other words, the only thing that we can see, which are the numbers that you saw in the first slide, you know, this 1/2, 18/7, square root of 2, pi, and even the monster number with the fraction, that weighs nothing. And we constantly deal with this fine dust. Now, let me focus ideas with a theorem. Right? You cannot have a mathematics talk without a theorem. Now, this is a theorem that came about not long ago. I think it was in the mid-60s, which somehow wraps everything up and explains this problem of invisibility of the number system. The fact that the number line that seems so familiar to us is far more mysterious than the dark matter in the universe. We just don't see anything that contribute in any positive way to the mass. So this theorem here is the following. The random numbers account for the total mass of the real number system. Now remember, what is a random number? A random number, so you can start from 0 to 1, right? So 0 point bunch of digits. If you pick up one of these numbers and you want to know the first million digits, well, I'm afraid I have to give this digit to you one after the other. Well, the first digit is 3, the second is 5, the third one is 0, fourth one is 0. It'll take me a year before I can communicate to you what that number is. You see, think of it that way. Suppose you want to communicate a number to somebody in another galaxy, and the phone call is very, very expensive. And you say, and you want to communicate a million digits. You say, it's the first million digits, first to it goes. But suppose you have to communicate the first million digits of a random number. Well, then it will drain your bank account. Because the first digit is 1, first digit is 2, 27 digits. You say, what did you say the third digit was? And you go back, and the situation would be very unsatisfactory. Now, what's the mathematics of this theorem? It's pretty devastating, actually. It's not just that the total mass of the number system is made by invisible number. It's actually a lot worse than that. These numbers are not visible because they can't be defined. They can't be talked about. They can't be computed. They can't be stored in a machine. And to add insult to injury, they can't even be proved to be random. Because if I give you one number, that suppose I'm God, and I give a number that is a random number, and I go, is it random? And then what I mean, maybe I'm dumb. Right? Maybe I just can't find this elusive, nice algorithm that will allow me to have a very quick representation of that number. And so, in fact, the theorem never talks about individual numbers. However, it is the power of mathematics. You can actually deal with the totality of the numbers in terms of weight, without actually having to mess around with this concept of randomness. Now, so what's the next question? God gave us the integers. We are in trouble. Well, does chaos exist? Now, why did I say that? Well, think about it. We have developed this toy model, and then we have discovered that if we can compute the present, then we can predict the future. And now we seem to discover that for almost all numbers, for all the numbers that count, we can't compute the present, therefore we can't predict the future. Well, in mathematics, we can only conclude that chaos exists, but it can't be observed. I cannot show you a kind of chaotic orbit, because in order to show you a chaotic orbit, I will have to put in the computer the orbit itself to begin with. I mean, then what kind of, the computer is simply giving back to me what I already put in. This is totally unsatisfactory situation. If I show you the jumping around of the toy model that start from the square root of 2, yeah, you know, you can watch something in front of your eyes. It looks very much like chaos, but it isn't, because that number can be calculated with great efficiency. And what about physics? So in mathematics, the chaos seems to be sort of out of our reach. But what about physics? Well, physics situation is even worse, actually, because there's no continuum. Right? This pencil drawing the line, it's complete fantasy. We know that when you get on a small scale, there is no pencil. Right? There are atoms, and you throw away the continuum and everything else. So there is no continuum. The above construct do not apply. People have been working very, very, very hard on what is called quantum chaos, and the quantum chaos is really not anywhere near as chaotic as this toy model, and I will try to get somewhat close to it a bit in the next 10 minutes or so. But so God gave us the integer. We are in a big mess. Whose fault is it? Well, it can't be God, right? So it's got to be somebody else. So well, I mean, really, I don't think the devil has anything to do with this. I think it's just a historical accident. What has happened? It happens that great guys like Euler and Gauss, they shape our understanding of mathematics in an unbelievable way, happen to be born before Bill Gates. And so these guys didn't have a computer. That's the point. If they had a computer, if we could rewrite history, mathematics would be very different. If you read Gauss and if you read Euler, you know that they would have loved to put their hands on a computer. They loved to compute. They were fantastically good at computing. But because they didn't have a computer, they never dealt with these monster numbers. You can't do calculation with a number with 3 million digits. You cannot even ask this question about randomness if everything you do is pencil and paper. You know, it's a completely different setup. So if we could rewrite history, then things would be a lot better, actually. And the mathematics that we will have developed would not be the kind of dark matter situation that we have seen. Who cares about these random numbers that constitute all the mass of the number system? Why do we have to deal with them? I mean, I know that if there are professional mathematicians here, then I'm going to get into real trouble. But you know, there is an important point here. I mean, we made the continuum of the number system. The point is that when you do integrals or you differentiate, then you do need the continuum, but you don't get anywhere near to having to account for the individual elements of the continuum. And what chaos theory did is to bring out all this evil that is buried in the number system. All in a sudden, the fact that we can't compute numbers becomes important. It's not important if you have to compute an integral. Somehow it sweeps over this continuum without really looking at the detail. But what chaos theory does, it keeps like magnifying stuff over and over and over again, and so it just exposed your own ignorance straight away without any hiding place. This is the sense in which Joseph Ford said that chaos is different. You are dealing with objects that simply cannot be manipulated by humans, and there is no smart guy than a year from now, or 100 years from now, or 1,000,000 years from now will ever be able to fix this problem. This problem is terminally unsolvable. So let's start from 0. God gave us an integer part 2. Okay, let's think about it. You know, I don't want to draw any. No, continue. Forget about that. So first of all, I'm not going to put the integers on necessarily. On a line. If I get the integers, I can put them wherever I want. I can put them on a circle. People have been doing this. I can put them on an array. I can put them in this bizarre structures which are called trees. Mathematicians are weird. I mean, if you see this, you don't say, oh, that's a tree. But mathematicians think like this. They say, oh yeah, of course it's a tree. Right? So what happens? For instance, a half. Why do you have to think of a half as something that is in between 0 and 1. I mean, half could be that. Right? Half is just two numbers. First one number and second one number. Then we agree that the first one goes on top and the one is below, but you don't have to put them in between 0 and 1. Now, what happens if you start thinking about these sort of structures? Essentially, you stick with the integers or with the fractions, but you don't try to fill the gap in between the integers and the fraction. You don't build dark matter. What happens? Well, first of all, we can construct, it turns out, a toy model. So there is a version of toy model that will operate. I'm not going to get into detail, just want to give you the idea that somehow we stay closer to God, so to speak, in order not to get into trouble. So there is no continuum. And because we will avoid this obsession of filling the gaps in between numbers, so we're not going to get into the sort of trouble. But it turns out that this approach is not going to be problem free. And I'm going to tell you something very interesting that happens if you follow this different route. Well, first of all, let's go back to the fractions. Now, just look at that 1 over 97. Now, Gauss started looking at the digits of fractions. And he understood that the heart of the matter were digits of fractions with the prime numbers at denominator. And he started computing them. And he computed the digits of the fractions of all fractions that have denominator smaller than 100. And this is the largest denominator that Gauss computed. This is when I say that Gauss loved computing. Well, you can see it there. How many people would sit down and compute all the digits of all the fractions? Now, why do I say all the digits? Well, it turns out that 1 over 97 has got 96 digits, one fewer than the denominator, that produce this unbelievable pattern that look pretty random, and then it starts repeating itself. So, in essence, all this number is capable of telling you is 96 pieces of information, right? 96 digits, which are really very unpredictable, and then it starts repeating itself. So there is a limit, and this is not a random number, because if you want to compute a billion digit of this number, you just take the first 96, which is a bit of work for that, but then you keep repeating that. So you get a sort of discount that will allow you to construct this sort of short programs. And this is called a pseudo-random sequence. When you transmit your credit card detail over the internet, the people that are in charge of keeping the information secure, they actually use this sort of principle. In other words, somehow embedded in the encryption of your credit card detail, there are information which are pretty close to sort of this nature. They have roughly this sort of structure, without telling you that the 1 over 97, which is the secret kind of code to figure out what the credit card number is. That is sort of the idea. So there is a form of randomness which is not randomness. There are plenty of smart programs that you can use, but somehow if I withdraw a little information about the smart program, then you won't be able to tell the difference between what you have, whether what you have is actually random or not random. They exploit the fact that it's a tricky business to spot a smart program. So the program to produce these digits has got some input, which is sort of the seed of the random sequence, which is just 1 in 97, and then there is an unpacking part of it, which turns out to be done through the toy model. It's a kind of version of the toy model. So you see, this is a different type of program. This program is actually smart, but it's actually slow. Why slow? Because you have to do this unpacking. And if somebody would ask you, I've got 1 over 97, suppose that somebody tells you these digits at some point will start repeating. When will they start repeating? it turns out that that is a very difficult question to answer. You know that they will start repeating certainly within kind of 96 steps, but you don't know how many. It could be 96, or it could be 96 divided by 2, it could be 96 divided by 3, etc. There are all kinds of possibilities among which you won't be able to choose. And in fact, there is just about one of the deepest problems recognized as the most important unsolved problem in contemporary mathematics, the so-called Riemann hypothesis, which is intimately related to predict the precise length of the digits of the fraction with prime denominator, believe it or not. So you see that behind this business of this pseudo-randomness, so numbers that are not random, because we can communicate what they are very fast. There is actually some very deep mathematics. So let me wrap up this talk by showing you where this all leads in the next couple of slides, and then I'll be finished. So we have spotted two ways of getting in trouble with predicting the future. Let's say that we try to predict the future of, let's say, our toy model, and we discover that there are obstructions to predictions because the program that we have to write to predict the future is just too big. And it's too big because essentially the input, which is our description of the present, cannot be computed. We have to give it. We have to put things inside the program explicitly. But there is another scenario in which the computer program, it's very small, like the one we see before. It's got this very simple input, but there is this unpacking problem. It takes time. And that happens if you don't try to fill the gaps in between the integers with the continuum. If you try to avoid the type of trouble that the Kolmogorov spotted, still there could be prediction to obstruction to predictability. So how long is too long? Well, we sort of know how big is too big, right? If the program is the same length as the output, if in order to produce the output we have to know it beforehand, then we know that that is a useless program. That is the Kolmogorov type of chaos. So how long is too long? Well, this is a very important point. It's a final point that I want to make. What's the difference between prediction and observation? So suppose that we've got this scenario. We've got a bunch of points, and we start from A, and there is this law of motion, these arrows that carries us around this maze. And now you ask a question about predicting the future. If I start from A, if the first frame of my film is A, will I ever be able to get to B? And if so, how long will it take? Now here, you have to appreciate that there are two possibilities. One, that you have a theory. And you say, okay, do a little calculation, and say, yeah, you can get there in 29 steps. But suppose that the only possibility is the following. Well, can I go from A to B, and if so, how long will it take? Well, just a minute. So, and now we answer the question, yes, you can go from A to B. It takes 7 steps. Let me just run this again. Can I go from A to B, and if so, how long will it take? Just a minute. Oh yeah, 7 steps. So you say, well, will it rain tomorrow? Just a minute. But in 24 hours, I'll give you the answer spot on. Suppose that the shortest program to predict the weather takes exactly 24 hours to give the answer, and you give it precisely. What do you do with your theory? You throw it in the dustbin. Right? So there is actually a counterpart to the Kolmogorov idea of dumb and smart, which is precisely what people use to create unpredictability. And I mentioned computer security it relies on the fact that there are certain computations where you think you have a theory, but you don't have it. You just watch things happening. And when things have finally happened, then you're able to give the answer. But this is not a prediction. This is actually an observation. And to wrap things up, let me quote again Joe Ford, that say the chaotic motion cannot be predicted. It can only be observed. So in spite of the fact that going from A to B, it's perfectly deterministic. There is no uncertainty. The future is connected to the present in a unique way. If all we can do is watch a computer program that give us the future, starting from the present, without really having a clue of what the computer program will do in between, then we are in real trouble. There is only one little hope, which is a big question mark actually, and it's quantum computers. One of the way in which my colleagues that work in quantum computing get big fat grants, but because they have discovered that if the program of quantum computing will work, then they will be able to beat this sort of chaos. The pseudo-randomness, the God gave us the integer part 2. And so what is happening right now in the physical sciences is actually important, very, very important implication that goes far beyond physics, and it feeds back into mathematics. It feeds back into very important unsolved problems about mathematics. However, this is a big question mark, and we really don't know how things will develop. Well, thank you for your attention.
Franco, we'll take one or two questions. We don't have much time because we're already over time, but if there's anybody who'd like to ask a quick question.
That's okay, we can do it in private.
Well, Frank will be here. If you'd like to ask him a question, in perhaps in a slightly less intimidating environment, he'll be here afterwards for a few minutes. If you're interested in going to the Centre for Mathematical Sciences, can I just say the way to go, the easiest way to go, is simply to go out the door at this side of the Institute, where I'm pointing now. That's the best way to go. There is going to be a table, as I said at the beginning, of memorabilia for the Institute, which you might like to look at on the way out. There's going to be on that table a tray for you to put in the Cambridge Science Festival feedback sheets. We filled one out. And can I thank you very much for coming, and welcome. Have a very good day.